record. So hello everyone, we are now in week 11. We are on the downside. We're almost done, 5 weeks to go, and some of you will never see me again. I feel so sorry for you. Yeah, Megan's very excited about that. That's
Not that, but like
okay.
5 semester, man.
So this is now going to be lecture number 21. The first 20 are all on my YouTube channel. Please like and subscribe. Thank you. And we are starting today by answering someone's homework question. I think, was it Molly? Was it you?
Yep.
So this is the normal model. I'm going to load up my questions here. And which question is it?
It's slide 18, question 5.
Slide 18, question 5. So let's go to slide 18, which is here. Hold on a second. Oh, yeah. Slide 18, question 5. Okay, so the distribution of the number of days of a normal human pregnancy is normal with mean 270 and standard deviation 9. Complete the graph of the situation. Well, I can immediately write down some stuff even before I read the questions.
Can I just ask my question about it? I mean,
Sure, go ahead.
Here's my question. It's kind of a wording issue.
Okay.
It's almost all of the data.
That's three deviations is almost all.
Right, 99.7, is that right?
99.7% will be 3 deviations, but in terms of how far you go, that's all the way to 297. That's 3 deviations to the right.
Right.
So
when I was answering that question on letter A, I put that. And then when I looked at the homework, it said that it was between 252 and 288.
Yeah, that's a 252 and 288?
Yeah.
Well, neither of those numbers make any sense at all. Wait, so -9. Oh, not 249. That was bad. 243, right? Yeah, so that's a mistake on whoever wrote those PowerPoints, because almost all is 3 deviations. Okay. And 3 deviations is 243 to 297.
Okay, that's what I thought.
Yeah, so that's good. So I always love it when, when you catch a mistake that someone else made and you're confident enough to really believe that it is a mistake. It shows that you have a deeper understanding. I always love that. So that's your question then, right?
That was my question. So that throws like everything else off, I think.
Yeah, so I think now, well, the part B and C don't really need the part A. So you should have been able to answer those without part A.
Well, okay, maybe, but here it says labor may be induced if a woman is 2 weeks late. So I'm wondering this standard deviation of 9, right?
Well,
for those days.
Yeah, one standard deviation is 9, but 2 weeks late, that's 14 days. So that's 284, right?
So it's like.
So we have a formula.
5,
well,
right?
Let's take a look. So the z-score is going to be our data, which is 284, 2 weeks late, right? Okay. Minus the mean, which is 270.
Right.
Divided by the standard, well, that line was straight, amazing. Divided by the standard deviation, which is 9. So you get 14 over 9. That's about 1.5 bar. So your z-score is a little over 1.5.
Right. Okay. So that's what I had. But in the homework, it said we should subtract 270 from 288 instead of 284. So
yeah. So I again, I these are not my PowerPoints. These are someone who made them for the entire course. So I apologize for them being wrong, but those are wrong.
Because 288 is 4 days over 2 weeks.
Yes, 288 is 2 deviations, but it's not what they asked. They said 2 weeks late. 2 weeks is 14 days.
Okay, good. Thank you.
Yes, good. I'm sorry. So again, sorry about their mistake that I never caught.
Okay. Sorry. Okay, I have another question.
And then of course, part C uses this z-score, not their z-score, so the numbers are going to be a little different.
Right.
Okay.
Okay. On slide 22, number 9,
Slide 22. Question number 9. Okay, in the Los Angeles Unified School District, the LAUSD, children who consistently exhibit the capacity for excellence at remarkably high levels of accomplishment far beyond their chronological peers may be given an IQ test by an LAUSD psychologist. The LAUSD uses the Wechsler Intelligence Scale for children, the WIX4, which is a mean of 100. That seems important, the mean of 100. And a standard deviation of 15. If a student scores at the 99.9th percentile, he or she is classified as highly gifted. Students who score at the 99.5th percentile may be accepted at a highly gifted magnet school if there's, of course, a seat available.
Okay.
So what is the lowest IQ score that qualifies as highly gifted?
So what I did for that is I put 99.5 because
No, that's a percentile. No,
right,
first of all, highly gifted is the 99.9th percentile.
right.
99.5th is just when they'll be accepted at this school, but they're not highly gifted necessarily until they're in the 99.9th percentile.
Okay.
Right? That's higher than this.
Okay.
Okay. And a mean of 100 means half the people score 100 or less.
Okay.
So if you score 99.5, you're actually below average. So what we need to do is we need to go from percentile to z-score, and then from z-score to raw score.
Yeah. Okay. I did all that. I just had a question about like that 99.5, you're accepted into the highly gifted magnet school. So I used that as a,
As being highly gifted?
yes.
When I read the question, I don't see it that way. When I read the question, I see highly gifted to be 99.9th percentile.
Okay. Got it.
Okay. That's how I read the question. But if I was grading this, I would certainly give consideration to someone who did that.
Okay.
Okay.
Thank you.
You're welcome. All right. Any other questions before we move on to bigger and better stuff? Going once. Going twice. So, okay. So let's now take out chapter 15. This is now the material that corresponds to what's going to be our third test. And this is now, where are you? This is now share screen. Okay. Analyzing bivariate quantitative relationships, scatter plots, and correlation. Yeah, we're excited about this one. Can I get a whoop whoop? Okay, so analyzing bivariate quantitative relationships. That's a lot of many syllable words in a row. 1, 2, 3, 4, 5, and that doesn't count. So basically 6 words in a row that have at least 3 syllables. Or yeah, that's heavy duty stuff. But let's see what it says. Analyzing. Well, we know what that means. That just means like, thinking about and trying to understand what comes out of it. Quantitative, that's just numerical. That's dealing with numbers. Relationships, that means the connections. Okay, that's not bad so far. Bivariates. Ooh, that's a word. Bivariate. What does bivariate mean?
2 variables.
2 variables. So we're looking now at relationships between variables as opposed to each variable by itself. And the method that we're going to use to analyze bivariate quantitative relationships are scatter plots and correlation. So those 2 things are things that you shouldn't know what they mean yet, unless you happen to have seen them before. But if not, scatter plots and correlation is going to be the content for this chapter. Okay, so let's take a look at this picture we have here. The x-axis, years of schooling girls can expect to receive, and on the y-axis, projected total fertility rates. How many children are there per woman? And we see a trend we see that the more schooling a girl is expected to receive, and it varies by country, the fewer children that that woman, as a general rule, is going to have. Not only do we have this relationship between those two quantitative variables, but we also have it structured categorically, where we divide countries into regions to see if there's any tendencies amongst, general areas, like in Europe versus the sub-Saharan Africa versus Middle East and North Africa versus the Asia Pacific type thing. So we're not analyzing the socio and economic aspects of this. We're looking at this solely from a statistical perspective. What does each dot on the scatter plot represent? Each dot on the scatter plot represents a country. Niger, Afghanistan, Chad, and so on. What are the two variables plotted for each dot? Well, their X variable is the years of schooling a girl can expect to receive, and the Y variable is the projected total fertility rate. So every one of those countries has these two quantitative variables as an average, and that's what we're plotting. How would you describe the relationship between the two variables? It seems just at a cursory glance that as the number of years of schooling goes up, the number of children goes down. Why do you think that might be the case? Can anyone think of some reasons why that might be the case?
Yeah, it's actually I studied this in a class last year. I forgot about. They're more educated on, for one, it's the whole idea of contraceptives, and a lot of those countries' religions didn't really believe in contraceptives, but now because they're becoming so overpopulated, it's getting to the point where it's uncontrollable and there's mass rates of poverty. So
Wow.
doing all that, educating them like, hey, do this, have birth control, all this stuff, it's going to limit them having 11 kids, basically.
Wow.
And the more schooling that they get, the more likely they are to actually stand up to forced marriages as well, and things like that, because they're much more educated on what options they have. Whereas, like, if a family sees their daughter or something, for example, as a burden and gets them married off very quickly, they're much more likely to have more kids at a younger age.
Those are all very logical explanations. Are there other ones out there? Who knows? But those seem very, very, very logical. From a statistical perspective, there's no question that there is a general trend here. And that trend is that as the number of years of schooling goes up, the number of children per person, per female goes down. Okay. I know. Okay. So I'm very excited. Now, when we talk about patterns like this, connecting two variables, notice that this is quantitative numbers and this is quantitative numbers. We only deal with quantitative relationships here with scatter plots. We do not deal with categorical, although we can include categorical, like using colors or symbols and things of that nature. But the x-axis and the y-axis must both be quantitative. And we're going to essentially be looking for 4 types of features of a scatter plot. The first one is whether or not the data appears to be linear. Does there appear to be a linear relationship between them? Okay. Now, in real life, nothing ever falls exactly on a line. We don't expect all the dots to appear perfectly on a line. But the question is, does it generally form a line? Is there a linear trend? And here I would say there is, right? In fact, there's a line that's kind of drawn through the data, which kind of represents it here. Okay, even though that line is artificially drawn, as we're going to see, there's a very specific line associated with each scatter plot that you can actually calculate. Once you've established that there is a line, the next question is, does the line go up or does the line go down? Is it a positive relationship or is it a negative relationship? This one seems to be negative, right? As one goes up, the other one goes down. So it's a negative slope. The third one is how strong the relationships. How strongly linear is it? Is it really strongly linear? Is it it's kind of linear? Is it like, I don't even see any linear there, right? Or we're going to see there's a number that you can assign to it that kind of answers that question. But Just in looking, is it strong? Is it moderate? Is it weak? Is it non-existent? These are questions that we might ask. And then the fourth one is there anything outside that just completely, is there an outlier? Is there something that just throws off the entire pattern and makes no sense together with everything else? In this case, I really don't see any outliers. There's nothing that just stands out and says, like if I had a dot up here somewhere, for example, up in the top right corner, that would be like, what is that doing there? I don't really see anything like that here. Okay, so those are the four things that we're going to be looking for. Okay, so the first one is, as the next one says, the linear relationship. Oh, someone said something. What did they say? They said that would be super. Okay, that would be super. All women are super. What are you saying, Solaire? Come on. All right, linear relationship. Okay, the word linear has a different meaning in statistics than in algebra, although not really. I don't know what that means. Well, I guess so. Okay, so in algebra, if points lie exactly on a line, we say it's a linear relationship. In statistics, if the points kind of cluster around a line, then we call it a linear relationship. Even though it's not a line, if it has a linear trend, then in statistics, we would call it linear. Okay. But just keep in mind, even when we use the word linear, it's not exactly linear unless it falls on a line, which it very rarely ever does. Okay. Sometimes you will have a relationship that is very nonlinear. Okay. So this one here, for example, this is a GDP per capita and life satisfaction on average, life satisfaction higher in rich nations up into a point. In other words, as the quality or the wealth of a nation increases, the satisfaction rating goes up, but not forever. Once you kind of reach a certain satisfaction, and even as you increase the quality, you know, the GDP, the economic factor that you're using to determine how wealthy the country is, it kind of tapers off and it kind of like levels out. So this is a non-linear relationship. Okay. For non-linear relationships, we do not use what we're going to be using in this chapter. Okay. What we're doing in this chapter is for linear relationship. Okay. So let's focus on linear stuff because that's the stuff that I really want to cover. Okay. So in this case, what does the dot represent? The dot represents countries. Again, here's the United States. The United States is the richest country, but not necessarily the one with the highest life satisfaction. Okay, we have countries up here, although I don't really see, what these specific countries are.
Professor, is it countries or is it the dots that are on the bottom that say advanced economies?
No. So all the colors, all the dots that are of this colors are all countries with advanced economies.
Okay.
And all the dots of this color are countries with emerging markets.
So regardless.
And these ones are developing economies and so on. So we're kind of throwing in a qualitative aspect to this scatter plot by looking at these dots and kind of grouping them to see whether or not there's a pattern that comes from the groups themselves. Okay. So in general, the higher the GDP per person in the country, the higher the percentage of people who are satisfied with their lives. That is, the relationship is positive. It's still a positive relationship, even though it's not linear. It's still going up as you go left to right. It just doesn't go up like a line. Another example of a non-linear relationship would be heights of people. If I were to measure babies from when they're born to when they're, let's say, 2 or 3 years old, what would I see as their age gets higher? What would happen to their height?
They get taller.
They get taller. Does that trend continue indefinitely?
No.
No, if it did, I would think that an 80-year-old would be like 900 feet tall, right? It doesn't continue that way. Heights taper off and you reach a certain height and then you just stop growing. That's just the way we are physiologically. I don't know if scientists have understood why or not. I don't know what they do. They just do fancy stuff and say, hey, I'm a scientist, so I don't know. Anyways, Why do you think the relationship flattens out as GDP per person increases? This is not really a statistical question. This is more of a socioeconomic question. And I have no idea what the answer is because I don't know anything about this kind of stuff. So we're going to skip it because I want to focus on the math. But you might have an answer. Maybe one of you does. Why do you think the relationship flattens out as the GDP per person increases?
Said up to a point.
Yes, but why? Why doesn't it increase forever? Huh?
Life satisfaction after a certain income bracket, I'm assuming, does not increase. So after you make a certain amount of money in your life and you keep making more, it doesn't necessarily increase the life satisfaction.
Well, I will have to try that. So I'm going to try to win the lottery, and then I'll get back to you, Solaire, on whether or not that's true. But
It could be
maybe.
because there's always that saying that rich people aren't happy all the time. So
Well, everyone has problems, but I prefer to have a rich person's problems than a poor person's problems as a general rule.
Me too.
Yeah, dealing with your problems with the money you got.
Exactly. Exactly. Just throw money at problem. That's the Lori Loughlin approach. Okay, strength and trends. Okay. So linear relationships can be classified as strong, moderate, weak, or none, but there's no set rules for this. Okay. You know, they're kind of hazy where they transition from one to the other. The first one there, would you say that's strong linear, moderately linear, or weak linear?
strong.
That's basically perfectly linear, right? That's as strong as it gets. You can't get much stronger than that. Okay. The second one,
Might be increasing.
yeah, my when I look at it, I kind of do see an increase as opposed to a decrease. That's my natural, my that's how it looks. But it's certainly not going to be strong or even moderate. I mean, it's weak
Yeah.
at best.
I think we also would say it was weak increasing, that like how we used to say it in our other classes for statistics. They would say if it was weak and increasing.
Yeah, well, this is certainly increase. Well, I wouldn't say certainly. This looks like it's increasing, weak at best, right? Certainly not moderate, but weak at best. The third one there, I don't even see anything. I don't see linear increasing. I don't see linear decreasing. I see nothing. That's non-linear at all. On the bottom right, that's pretty strong linear, although it's decreasing. The one in the middle is increasing, I would say moderate. And the one on the left is decreasing and moderate strong, somewhere in between. Again, we're going to have numbers for these. So these are just, you know, the
Speculation.
yeah, these are just like what it appears just when I look at it.
Professor, the one at the middle, the one on the middle bottom row,
The one in the middle bottom row, yeah.
that would be
Moderate
moderate
increase.
increasing.
That looks like to me moderately increasing.
Okay.
Yeah, I wouldn't call that strong. Yeah, moderately increasing seems appropriate. But again, I can show you the same graph, and I can show it to you with two different scales. You know, this is 1 to 6, 1 to 6, but I could show you two different scales, the same graph, same data, and you might say it's moderately strong for one and weak for the other, and because your eyes are very easily deceived, which is why we have mathematical techniques that do it for us, right? So these are just our basic assumptions when we look at it, but just be aware that the eyes can deceive you, okay? So example, Hershey Park in Pennsylvania contains some of the most famous roller coasters in the eastern United States. The scatter plot shows the relationship between the track length, that's in feet along the x-axis, and the ride time in seconds for the 11 roller coasters in Hershey Park. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, I see 11 dots. Okay. Circle the dot that represents the roller coaster that you think is the most terrifying ride.
I want to say the one at the very top.
That's what I was thinking too, and only just because like it's almost 3,000 in length, but it's like a whole minute and extra seconds. And if you're terrified of roller coasters, that's a thing that plays into it.
I would say the one at the bottom,
Which one at the bottom?
all the way at the right.
Yeah, so the one at the bottom is the longest and the shortest time, right? That means you have to get to the whole thing fast, right? You're going a very far distance and you're going there quick.
But it's over in like
Yeah, I would say
Well, okay. So
Yeah, but it's like further.
terrifying is
I guess subjective.
Objective.
it's a subjective thing. For some people, you know, like when you see something scary like a jump scare, you know, jump scares don't last a minute, right? That kind of defeats the purpose. They're quick, right? So it is subjective. But my personal guess would be the bottom right. Okay, it's the longest and it's the shortest, so it's quick. You're going the fastest. That's probably how they that's just my guess. Okay, that's my guess. Well, here we can do it. Ready? We can someone do a Google search. Sky Rush in Hershey Park. Let's see if it even comes up. Sky Rush in Hershey Park, and see if it comes up with a track length or anything like that. Oh, a Telegram group. What's a Telegram group?
Talking about the last dot on the right, right?
The bottom right is what I would call the most. What I would subjectively think is the most terrifying.
So
because
the
it's long.
track length.
Yeah.
Okay. So it says the max speed is 75 miles an hour, and in height it's 213 feet.
But it doesn't give track length or time.
It doesn't really give track length or time.
So there's really no way of knowing it. Okay, bummer.
Oh wait. Ride time says a minute. And
Okay.
ride length 3,600 feet.
There it is, bottom right. 60 seconds, 3,600 feet, give or take.
I'm
You
not
get
scared.
a force of 5 on that ride.
What happens?
You experience G-forces on that ride.
A 5. That's a lot. Okay. So what is the track length? 3,700 feet. Hard to say, but we just looked it up. What's the ride time? About 60 seconds. What's the relationship between track length and ride time? So as a general rule, is there a trend here between track length and ride time?
I feel like this is one of those things that has no correlation because it's subjective. People have different fears. So
It doesn't have any, it doesn't seem like a strong linear correlation.
Yeah, well, first to say what Megan was saying, yeah, some people it's about height, right? The higher the ride, the more terrifying. So some people it's about G-force. Some people it's about how many twists there are. I mean, it is completely subjective.
yeah, based on this scatter plot, it just seems weak. Like there's no weak but increasing or weak but decreasing.
I don't really see any pattern here at all.
So non-linear.
Yeah, this does not look linear to me at all. Yeah, basically there is no relationship essentially. That's basically the relationship. You know, you have fast ones that are short, you have fast ones that are long. You have short ones that are short and you have short ones that are long. So this really doesn't look like there's a relationship here. Okay. Our major what we're going to spend most of our time on is the linear ones because we can do math on those and those math can give us answers that kind of make sense. So example, to study the factors that affect student success, CSUN conducted a study of the high schools that send 25 or more students to CSUN per year. For these high schools, is there a relationship between the average SAT verbal scores of entering CSUN students, that will be the y-axis, and the percentage who get a grant or scholarship, that will be the x-axis. And a scatter plot with a summary line helps us see the answer. So the summary line is already there. And even if the line was not there, if I asked you to draw the line that you think best fits this data, you'd probably draw something in the vicinity of that line, correct?
Mm-hmm.
That line seems to basically, come across the data in a very representative way. So more students come from Granada Hills GH than any other high school. 41.1% of Granada Hills students get grants or scholarships, and their mean SAT 5 score is a 491. Circle GH on the scatter plot. Well, they gave us the X and the Y value. So all we got to do is find it. The 41.1 is about here. And 491 is about there. I think, would you guys agree with that one?
Yeah,
Yeah.
All right, that's the Granada Hills right there.
they're nasty.
Sorry,
Oh, I call it Granasty.
is that where you went to school?
The first 2 years, and I hated it.
So it's Granasty, and now you're in Seasucks. Okay, got it. Okay. I just made it up on the spot. That was
Is
crazy.
that really what they call? That's so unclever. There's so many CSU things. That's so unclever. Okay.
Damn. Okay. How do you really feel?
No, I thought like you. I didn't think you'd make it up, but I was like, is that really what they actually call it? Because
No, I just made up on the spot. I don't know. I don't know. I listen, first of all, I went to CSUN. I got both of my masters there, and I've been teaching there for like 15 years now. I think CSUN's a great school. If you're there for an education. So I was just kidding. I just thought it was funny. So that's the record saying that.
Yeah.
All right. So circle the terms that best describe the relationship. First, shape. Is it linear? Is it curved? Or is it neither?
Linear.
Linear.
Generally seems to be linear to me. Okay.
No.
Are there any outliers?
Yeah.
Is there any dot that is just like, what? This is crazy.
Oh, like way off the line or just
Yes.
slightly?
Is there something so far off the line that it's kind of like this does not belong with the data?
Nah.
No, I don't really see any. I mean, even the dots that are a little off here, it's not really so off the line. I would say none. Again, that's subjective,
Decreasing.
it's certainly decreasing.
Thing.
And would you say it's strong, moderate, weak, or would you say maybe it's strong in some places and moderate in others and weak in others? Does it vary? Let's ignore that one. Is it basically strong, moderate, or weak?
I said moderate.
Moderate.
Strong and moderate.
So they actually give us the R squared value. We're going to learn what that R squared value means. And we're going to see that an R squared value of 0.822 qualifies as, I'm pretty sure that's moderate. I think strong is 0.9 or higher. I think it's subjective, not subjective, but it's not like, and God said, let 0.9 or higher be strong. It's not like that. It's just these guidelines. And I think that R squared value corresponds to 0.8.
So if we said strong, we'd be wrong.
Well, if somewhere in one of these slides, they actually give us the guidelines that this class should be using, and those guidelines say 0.9 or above is strong, then yes, it would be wrong. If they don't, then if they just want a visual one, then I would not take off credit. Okay, we'll see as we go along. So conclusion, okay, sorry, not conclusion, correlation. So the correlation is how strong of a linear trend there is. Okay, how strong of a linear trend there is. If it's very strong, in fact, if it's perfectly strong, in other words, if it's a line, if all the dots are along a line, whether it goes up or down, then the correlation is 1 or -1. 1 if it's going up, positive, and -1 if it's going down, negative. Okay?
Sorry?
Correlation is always between 1 and -1. Okay, 1 and -1 are strong, strong, strong relationships. Okay? If it's perfectly on a line,
Slope is 1.
it's a
Or
no, not the
-1?
slope. Not the slope is 1. No, nothing to do with the slope, because slopes can be greater than 1. The correlation, which is not something that I've given you a formula for, the correlation maxes out at 1. If all the points lie in a line of positive slope, the correlation is 1, no matter what that slope is.
Okay.
And if they're all on a line of negative slope, the correlation is -1, no matter what the slope is. And all other correlations are somewhere in between. So the closest or the closer the correlation is to 1 or -1, the more strongly linear it is. The closer they are to 0, the more weakly linear it is. Positive correlations up, negative correlations down. So this example here, if we had to guess which of these was the appropriate correlation for this problem, first, which of these two will we throw out immediately?
The negatives.
The negatives, because this one goes up. So that means that the correlation has to be positive. Now, 0 means no relationship, no linearity at all. 0.2 is weak, and 0.9 is strong.
I would say it's 0.9.
So yeah, this is not weak or non-existence. This is certainly 0.9 if it had to be one of these three.
That kind of looks like our previous one.
It does a little bit, doesn't it? Although this is ice cream consumption with temperature. As the temperature goes up, does the number of ice cream eaten by a person go up? Personally, I would be up here no matter the temperature. That's,
Buy ice cream in the cold and in the heat.
that's ice cream at any time. Okay, group
That would-
activity. Like Dippin' Dots, right? Match each scatter plots with its correlation. Match. Oh, by the way, Molly, thank you very much. Now I understand what they are. She sent me a picture and I couldn't open it for like a day because I don't know what was happening with my email, but finally I did, and bam, Dippin' Dots sold here. So if I ever cheat on my diet or take a day off, I'm gonna get that address from you, just so you know. Okay, it's a group activity. Match each scatter plot with its correlation. So 2 of these are negative, 2 of them are positive, 1 of them is 0. Okay, so let's do the positives first. Of the 2 positives, we have extremely strongly positive, so close to 1, very strongly positive, and somewhat moderately or even weakly positive. So first we look for slopes. How many of these have positive slopes?
C and B.
C and B, right? This goes down, and this is what? So of these 2, which one has the stronger linearity?
C.
C. So 0.95 would be C, and therefore 0.5 would have to be B. If we now do the negative ones, same idea. We'll look for the 2 that have negative slopes.
A and E.
A and E, which of them would be stronger in terms of how tight the points are about a line? E, so E is this and A is this, leaving D as the one with no linear relationship. And yeah, when you look at it, there's no linear relationship. So that's fairly straightforward, correct?
Mm-hmm.
All right. Okay. I hope. Okay. Now, computing and interpreting the correlation R. Algebra 1 Common Core Standard is compute and interpret the correlation coefficient of a linear fit. We have to be able to compute it. How do we do that? Well, here's an example where we have 1, 2, 3, 4, 5, 6, 7, 8 points. 1, 2, 3, 4, 5, 6, 8 points. Okay, good. X-axis is height, y-axis is arm span. You expect as people get taller, their arm spans get larger as a general rule. Okay, of course, it's not going to be perfectly linear. That's not just the way humans work. There's always going to be some, some error in that, correct?
Mm-hmm.
So what we have here is a pretty linear relationship, positive or negative.
It looks positive, yeah.
All right, I'm throwing out that one. 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 Is it perfectly linear?
No.
I'm throwing out that one. I mean, can you recognize that there even is a linear relationship?
Yes.
Yeah.
Throwing out that one. So then the question is it weak, moderate, or strong?
Weak. Weak.
Oh, I don't know about that, guys.
Moderate.
It's either weak or moderate, but I wouldn't count 0.93 at all.
Personally, I think it's fairly strong.
I think it's moderate.
Oh, really? We got a battle here. All right, so here's what we're gonna do. We're gonna compute it.
Oh gosh.
Okay, so I'm gonna take out my trusty TI calculator. And what I'm gonna do is I'm gonna go to my data editing. And in the first column, I'm gonna put my X values, which are height. That's 162, 184, 173, 181, 162, 175, 192, and 192. Let's make sure I didn't skip one. Okay, I got all 8 of them. So my first column are all of my X values.
Mm-hmm.
And then I go to my second column. I got 161, 196, 177, 188, 159, 178, 194, and 188. Okay, in my second column, I got all of my Y values. And then I go to stat, calc, one var stats. Oops. Yeah, one var stats. And I hit a couple calculation buttons. And no, I want two var stats. What am I thinking? This is not one var. This is two var. Come on, you're better than that. Two var stats. And I don't see R. So let's go to this one and let's do that one. Now let's see if this one gives me R. And it does. So when I have my calculator compute R for me, the very bottom row, could someone read out that R value, please?
0.93085. So it is 0.93.
Yeah, look at that. We got a 0.93.
I knew it was
I'm going to
strong.
apologize for doubting me. I will accept them now for the next 8 seconds.
I apologize for doubting you.
Okay, I appreciate that. Megan, I didn't hear anything from you.
I apologize.
That's okay. I forgive you. All right. So, but the point is that it's hard to judge these things. So we would like to come up with a way of doing it. And it says here, compute using technology. So you don't got to know the formula. You just got to know how to do it on a calculator. But if you don't have a calculator, well, what else we got here? Let's take a look. We have computing correlation online. Now let's see what they say. First, let's remove this.
I think you might be able to do it on Desmos, but I don't even.
You could definitely do it on Desmos. So this is the formula, by the way, but we're not going to use the formula. Take me to the calculator, to the map mode. Oh, look at that. We got X values. Okay, 162, 184, 173, 181, 162, 175, 192, and 192. I don't think I skipped any. 161, 196, 177, 188, 159, 178, 194, and 188. Calculate R, and it gives me, oh, look at all this data here. First of all, it gives me a graph. It gives me all the intermediate steps. And here at the end, it gives me R. The value of R is 0.9309. So look at that. Quick, what did it take? Google search, R calculator online, the very first link, easy to use. I have no follow-up here, so period, exclamation point, let's keep moving. Okay, so they interpret the value of R in context. So there's someone laughed. Who laughed? Someone laughed. Ha ha, someone said. Oh, just ha ha. Ha, 3 ha's. Oh, that's like one more than normal. I love it. Okay, so what we have here is a strong, very strong relationship between height and arm span. Very, very strong relationship. Okay, I'm not going to use the number 0.93 as well, 93% or 0.93 this. We're not going to worry about that. The number just represents the strength of the relationship. Okay, it is a very strong relationship. 0.93 is very strong. Okay, so, some pornography, I apologize. Okay, so correlation and the units of measurement. So it says convert the missing measurement to inches. So here we have arm span and height in centimeters. And here we have arm span and height in inches. And somehow we lost some of our data. So how do we convert 177 centimeters to inches?
Google.
Wow. Okay. Google is there, that's correct. But is there a better way of converting? Huh?
Isn't it a proportion?
It is a proportion.
When it's 2.54 centimeters. So wouldn't you put, is it 2.54 over? Are we looking at 177? Is that what we're looking at?
Yeah.
We would put 177 centimeters over X equal to 2.5 centimeters over 1.
Well, let's take a look. 177, which is centimeters, is the unknown number of inches.
Oh, yeah.
is the same ratio as 2.54 centimeters
Over 1 inch.
is to 1 inch. Right? So then I would cross quite so there. I would cross multiply and then divide. So x equals 17 points, 177 divided by 2.54, which is 69.7. And the question is, if I were to calculate the correlation using these values instead of these values, would I get the same value? Would I get the same number?
Hmm.
And the answer is yes, you would. Because you're measuring essentially the same quantities. The units don't matter when it comes to, the units do not matter when it comes to correlation. Okay, so if I were to go and use these numbers instead, I would get the same value. In the interest of time, we're not going to, oh, I can just do this, but you would get the same values. Okay, so does changing the units of measurements affect the, well, you know what the hell, let's do, let's just do it. Okay, so we'll use the calculator one. Okay, so we're gonna go back here and we're gonna go back a step. Okay, so hold on, let me move this over. So the X values are new. They are 63.8, 72.4, 68.1, 71.3, 63.8, 68.9, 75.6, and 75.6. And here we have 63.4, 77.2, what was it, 60?
69.7.
69.7, 74, 62.6, 70.1, 76.4, and 74. Calculate R. So you'll see it's a little different because we rounded. Some of these numbers are rounded. So it's not going to be exactly the same, but it's still basically the same. Okay. So to answer this question, does changing the units of measurements affect the correlation? The answer is a big fat
No.
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 Okay. And in fact, look at these graphs. This one is height versus arm span, centimeters and centimeters. This is height versus arm span, inches to inches. The graphs look very similar, don't they?
Mhm.
This is inches to centimeters, and this is centimeters to inches. And again, the graphs look the same. Because you are correlating the same quantities. The units do not matter. Now, does changing the X and Y values affect the correlation?
Yes.
Well, let's
Yes.
take a look. Let's do this one just for fun and stuff. Does changing the X and Y values. So let's go back here and let's see if I can cut and paste this. Oh yeah. Okay, so what we did here is we replace the X and the Y, and let's calculate R now. And we get, what do we get?
0.9293.
Which says what? That it's the same thing, isn't it?
Yeah.
So not only do the units not matter, but
Okay, answer is
I could even go so far as to change the X and Y values and it won't matter. So the correlation doesn't matter whether you do X to Y or Y to X. It does not matter at all. Fantastic stuff. So we've talked about linearity, we've talked about strength, we've talked about positive, negative. So now let's talk about outliers. So in a scatter plot, there's 3 possible types of outliers that can occur. Okay. It can be an outlier for the one variable, but not the other. It could be an outlier for both variables. Okay. Or it cannot be an outlier when either one is considered independently, but be an outlier when they are considered together. Okay, and we're going to do some examples to show all three of these. Okay, so example, the scatter plot on the next page gives the weight in pounds and length in inches of a large sample of black bears. For each point A to E, tell which type of outlier it is, then describe the bear. Which reminds me of one of my favorite riddles. Now, if you've heard this riddle, don't answer it. You know, hey, don't say, oh, the answer is this, because you already know it. That's not like, you know. So here's the riddle. A man leaves his house and travels 1 mile south. He then travels 1 mile east and then 1 mile north, returning back to his house. A bear approaches. What color is the bear?
Can you say it one more time?
Sure. A man leaves his house and travels 1 mile south. He then travels 1 mile east and then 1 mile north, returning back to his house. A bear approaches. What color is the bear?
How the hell did he get back to his house? Good question.
You missed going west.
No, I did not miss going west. You missed
But
the
how
point
did
of
he
the
get back
riddle.
to his house? He went south, east, and north. He didn't go back west or
That's
back
right.
south.
And there's one location on the planet where you don't have to do that.
North. Oh, is it up?
Oh, it's a pole.
It's a polar bear.
Okay, okay, I get it.
Okay. If you're at the North Pole and you go 1 mile south, 1 mile east, and then 1 mile north, you're back at the North Pole.
Got it. Okay.
Wow.
Yeah, that's
I was
right.
about ready to say like a black bear, a brown bear.
Anywho, so the scatter plot on the next page gives the weight in pounds and length in inches of a large sample of black bears. For each point A to E, tell which type of outlier it is, then describe the bear. So here we have a large sample of black bears. Now, these guys here seem to be the general trends. And then you got this guy out here, this guy out here, here's the guy, see, you got 5 guys that are out there, correct?
Yep.
So remember the options. You can be an outlier for this variable. You can be an outlier for this variable, or you can be an outlier for both. A, which variable or variables would A be an outlier for?
Probably weight.
Just wait, because its length is perfectly valid. It's in the realm of the data.
I would
Right.
say both.
So it's a variable that it's an outlier for is a weight, right? For that length, its weight does not make sense.
Mm-hmm.
How about B?
Same.
Same thing. For that length, which is a perfectly valid and normal length, this weight does not make sense.
Well, can't you say vice versa? For that weight, that length doesn't make sense.
Yes, but yeah, that's a good point. That's a good point. Yeah, if you look at it from this length perspective, then this weight is too much. If you look at it from this weight perspective, then this length is too little.
It jives.
It jives. That's a good point. I don't have an answer for you. I don't know. That's a good question.
Well, then you look at it from the x-axis point of view.
Huh?
Well, just to save confusion, we usually look at things from the x-axis, right?
Yeah, but this C, I would definitely say is a length outlier, right?
Yeah.
This B is definitely a weight outlier. There's no question on that.
Mm-hmm.
E is definitely both.
Right. So I would say A is both.
But A is not. Well, A is. Oh, I know what it is. It's not an outlier for either one individually, but it is when you look at them both together. This length is perfectly valid. Lots of them have that length. This weight, perfectly valid. Lots of them have that weight. But when you look at them together, length and weight, then this one here doesn't make any sense.
So it's an outlier for both.
It's an outlier for both. Well, but again, it's an outlier for both only when you look at them both together, not when you look at them both individually.
Okay, so outlier.
Okay, so that's category 3. Does that make sense?
What, and we said D was length, right?
D would be the same. No, D would be the same thing as A in that its length and its width individually are perfectly fine.
Got
Lots
it.
of them have that length. Lots of them have that weight. But when you look at length and weight together, this
Mhm.
one makes no sense.
So then A,
Okay.
D, and E are both when you consider both variables.
Yeah, so A and D are when you look at it jointly. B is an outlier for weight. C is an outlier for length. And E is an outlier for both. Not
Okay.
just jointly, but even individually. E's weight and its length, even by itself, E would be an outlier.
It's a big bear.
That's a big bear. Okay, that's Yogi Bear. Hey, boo boo. So, A and D are joint outliers. It's only when you look at weight and length together that they become outliers. B and C are individual for different ones, and E is for both. Okay, so hey, I learned something today too. That's great. Okay, independent and dependent variables. So we learned that the correlation doesn't matter which one's X and which one's Y, but which variable should be X and which one should be Y. So sometimes either way is fine. But sometimes one really depends upon the other. Like for example, if I'm looking at GPA versus how much you study, it's probably more likely that the studying affects the GPA versus the other way around. Maybe as a ramification, like, oh, my GPA is bad, let me study more. I mean, yes, and you can always do it the other way. But I think it's more reasonable to say that the independent variable, the one that you get to pick what it is the x-axis, and the dependent variable, the one that responds to that, is the y-axis. Okay, so looking at the following examples, was the right choice of X and Y made, or did it not matter? So we had an example above, years of schooling versus fertility rate. So does the years of schooling affect the fertility rate, or does the fertility rate affect the years of schooling?
Years of
The
schooling.
years of schooling affects the fertility rate.
So we did that one correct. For Hershey Park, did the length affect the time, or did the time affect the length?
Neither.
Neither. And in that case, either one is fine. Arm span, did the height of the person affect the wingspan, or did the wingspan affect the height?
The height
The
affects the
person
wingspan.
affects the
Right. I mean, that's the way you think of it. Height affects wingspan. CSUN high schools, what the hell was that one again?
That was the Granada question.
Right. But what was the percents with scholarship versus the SAT scores?
Mhm.
So this one, I think it actually be backwards, no? If the SAT scores are higher, that should indicate more, or I guess lower scholar. Let's see, what is this?
Related. Are they related?
Well, R squared is 0.822. That's pretty strong. That's an R value of 0.9. That's a strong relationship.
So average SAT score would determine grant or scholarship, probably.
Right, but as the SAT scores go up, the people who get scholarships go down. You know why?
Why?
Because people with higher SAT scores don't necessarily go to CSUN. They'll go to Harvard. They'll go to Yale. They'll go to Berkeley. No, I'm not saying CSUN's a bad school. I'm saying
What happened to
I'm saying there are significantly better schools that any one of us could have gone to, and we all know it. Okay.
I'm just kidding.
Yeah, if you think that, you're in the right place. Let's put it that way, huh?
Those tuition rates, though.
Yeah, those tuition, exactly. No, listen, there's some
How
very
can you-
smart people at CSUN. I have some students who have gone on to get PhDs who went to CSUN, and it's like, dude, you could have gone to such a great school. It's like, yeah, but my family was here. I had to help support them. I couldn't afford this. There are reasons why people would go to CSUN, 100%. But CSUN's also a commuter school. It's a school for people in the general area. It's a Cal State system, not a UC system. So their mandate is different. Okay, so there's no question that really, really good students tend not to go to CSUN. There are better places for them. Okay, if you're a scientist, you go to MIT, you go to Caltech, Princeton, Harvard, Yale. There's some great schools. So my point is that higher SAT scores, you're going to have fewer with scholarships because they're not necessarily going to need them at CSUN because they're not going to go to CSUN. Maybe that's a trend. I don't know. I'm just making it up as I go along. Don't want to get myself in trouble here by saying anything bad about CSUN. I still love the school. I've been here for a long time. Single parent high school graduation rates, huh? How about single parent and high school graduation rate? I don't remember an example like that. So let's
I
pretend
don't
we
even
did it for the
remember
first
that
time.
example either.
Huh?
I
Would
don't.
the single parent be? Would the single parent be on the x-axis and high school graduation rate be y?
Well,
I'm assuming that they're dependent.
well, you would think, right? I mean, what exactly what are we measuring on the x-axis for single parent?
Yeah, that's
Like
weird.
people that live in a single
One or two
parent
parents.
household have-
Well, but that's not really a quantitative variable. That's a categorical variable. You know, those are the first category versus the second category. We need a quantitative variable for single parent. Maybe the percent of single parents at different high schools compared to the percent of high school who graduation rates. So
Okay.
if we have, if 11% of the women in this school are single parents, or the men are, well, that's not really. Does that happen?
Yeah, it could happen.
Yeah.
Could happen. Okay, so let's say 11%. Yeah, no, it could. I mean, anything could happen. First of all, a mother can unfortunately pass away in childbirth, and the father has to raise it. There are reasons why it might happen. So let's say there's like 11% a single parent rate at this high school. Well, how does the high school graduation rate for is that affected? I don't know, something like that. So what would there be an X versus Y relationship here? Or would it be neither?
X versus Y relationship.
Relationship,
How you think there will be?
probably.
So
Probably, but which one affects the other, or does it not matter?
The being
Like
a
single parent.
single parent affects the graduation rate.
Affects how much graduate?
Yeah.
Yeah,
I would think so. That makes sense. And what about ice cream and temperature?
definitely.
Does if you eat more ice cream, does that mean the temperature goes up? Or if the temperature goes up, does that mean you eat more ice cream? Or vice versa?
Or ice cream melts at higher temperature.
Okay, you know what I meant. Okay. Now, this is a very important, this is probably the most important thing you can get from this lesson. Association does not prove causation. Just because things are associated, because things are connected, does not mean that one causes the other. For example, among all elementary school age children, there is a positive correlation between the length of a child's foot and his or her reading level. Children with bigger feet read better. What is the best explanation for this association?
Not
Why
a
do
clue.
children with bigger feet read better, huh?
Not a clue.
Yeah, I have no idea.
Because children with bigger feet are probably older.
Right? Yeah.
And because they're older, they're probably a few grades past the other.
Oh,
Oh my
okay.
gosh.
I thought it just meant like if you have one 5-year-old and another
I
5-year-old.
know, but instead of
One
like
has, like, a
all elementary school age children.
One has like a huge like butt. The other one,
Right? Hey, Bigfoot, come read the encyclopedia. You know, something like that.
he reads a lot. He's got a
Yeah.
big butt.
So reading better, does reading better causes children's feet to be bigger? Does that make sense?
No,
No.
Okay.
No,
Does having bigger feet cause children to read better?
no.
no.
No. Is there a lurking variable, something lurking behind the scenes that's responsible for both?
Yes.
Yes.
Yes. And that will be age. Here's another example, one of my favorite examples. It is a statistically proven fact that people with more cars tend to live longer than people with fewer cars. Families or people who own more cars tend to live longer than people who do not own cars or do not have many cars. Does this mean that if I want to live longer, I should go out and buy 3 or 4 cars?
That's how they get
Does it
you.
mean that you have more money than the average person?
And therefore, what does having more money do when it comes to living longer?
Not in poverty.
I have better health care. I have better access to doctors, right? There's all these different reasons why I might live longer. There's a lurking variable behind the scenes. So just because things are associated does not mean that one causes the other.
Are we looking at because I'm kind of going back to what we've been doing.
Yeah.
Are we looking at it as like a linear, like if it has linear relationship or
Well,
not?
linear or not, we're not even worrying about that right now. It could be linear, it could be non-linear. It's
Okay.
just, is there a connection?
The correlation. Yeah.
Yeah. So association does not imply that an increase in one variable causes an increase or decrease in the other. Often an association between two variables can be due to a lurking variable or even to a coincidence. Okay, a lurking variable is a variable that you did not include in your analysis, but that explains the relationship between the variables that you did include. If I look at cars and life expectancy, if I look at reading ability and foot size, I am not looking at another variable which matters. Wealth in the first example, age in the second example. Here's a plot that shows the results of tests of a test on fractions and weight of randomly selected students from a middle school. So here are their weights and here are their test scores. People who are heavier tend to do better. That's why I'm great at math, right? People who are heavier tend to do better. Does that mean if you want to do better and better in math, you should go to eat a lot?
No.
So why are people who are heavier, why are they scoring better?
There's a third variable.
Which is what?
I have no idea.
People who are heavier tend to be older. As you get older, you get taller, you put on some weight, right? 8-year-olds are not the same size as 9 and 10 and so on, right?
Yes.
I see.
Okay. So for each example, discuss whether an increase in the value of one variable would cause an increase or decrease in the value of the other, or whether there is a lurking variable causing both. And if possible, if there is a lurking variable, name it. So education and fertility in Muslim majority countries. That's the first example that we started with. Is that causation? Or is there a lurking variable?
Maybe a lurking variable?
Okay, well, what would you say if it was a lurking variable?
Like some of the examples people said before about education on contraceptive.
Yeah, but that's education, right? That's what we have here. Although it's not necessarily, I mean, when you go to school and your regular curriculum usually doesn't, well, sex education, I guess, is a class that people take, right? I never went to a public high school. Huh?
What's the question again?
Well, someone mentioned education about contraceptives, and I started by saying, well, that's not really the education that we're referring to. But then I realized that, I mean, I went to a very religious school. We did not have a sex ed class. But I'm guessing if you went to a public school, they probably did, correct?
I mean, we had health, but they could only go as far as like, it depended on your teacher, because some teachers were like, I'm not going to teach you about this stuff.
Yeah, so.
But they like, it basically taught you like STDs and everything, like, be safe.
Could a variable be that because they are spending more time on education, there is less time for child rearing, so time is the factor?
It could be. Yeah, listen, I'm not saying you're wrong. It could very well be.
Or maybe they have jobs that keep them, you know, away from like more of a career, you know, and that prevents them from getting into child rearing.
Could very well be. I really can't say. I don't know. I'm sure someone who is more in tune with this field would have an answer. I don't have one. I don't know. This one I think I can do. And miles per gallon and weight of car. We see that as the weights of cars go up, the miles per gallon goes down.
Yes.
Oh, that's
okay, because as you know, the car uses gas to move the car forward. It has to work harder if the car weighs more, right? So it probably seems very reasonable that one literally causes the other.
Okay. So what's the answer?
Sorry?
What would we put under that one if it?
I think it's a causation. I think an increase in weight causes a decrease in the miles per gallon. Yeah, that's what I would think. So quickly, each of the following is caused by a lurking variable and identify it. There's a strong positive correlation between the number of doctors in the state and the number of deaths per year in the state.
So that means there's more deaths if it's positive?
Yeah, more doctors, more deaths. Does that mean if you want to live longer, you go to a state with no doctors? What is the lurking variable behind the scenes that's connecting them?
Isn't it just because I guess like the more doctors, the more patients they can accept, and the more patients that unfortunately pass away under their care?
Yeah,
Population.
I mean, I'll think population, right? More doctors usually means more people live there. More people live there, people are going to die more, right? That seems to be the most obvious. Yeah, that's correct. Okay. Many parents have noticed an association between the child's consumption of sugar and hyperactivity.
Causation.
Well, they're saying each of the following is caused by a lurking variable.
Oh.
So what will be the lurking variable between sugar consumption and hyperactivity?
Children that are actually diagnosed with things like ADHD, maybe with hyperactivity.
I don't think that's what they're asking for, right? If you were to graph, children and consumption of sugar on one axis and hyperactivity on the other, would you think that the more sugar you have, the more hyperactivity?
No, you might crash at some point.
Yeah, I was about to say there is a crashing point.
Or maybe it's a emotional thing where if a child's eating sugar, it's usually something that tastes good, so they're in a better mood, so they're more hyperactive. It's not necessarily the sugar.
I don't know. That's a good question. I have no answer to this. I don't know. That could be. What do I know? I just teach math. I don't actually know it. All right. The CSU has found that students who take more math in high school do better in college. So CSU's Academic Senate, which represents faculty at all 23 campuses in the system, approved a resolution calling for entering freshmen to take 4 years of high school math rather than the current 3. Why do people who take more math in high school tend to do better in college?
They're
The
more
people
prepared.
that take more math liked doing math.
They don't take better at math in college. They just do better in college.
They're more college prepared. I don't know.
Why? What is it about math?
I guess like in terms of maybe finances and everything.
Is it logical reasoning, or?
Logical reasoning?
Critical thinking.
Maybe people who take more math in high school just take more classes in general. Not just math. They just like school more, right? They just like education. They're weird, right? They like learning things. They like being smarter than your peers, right? They like making fun of them at parties, saying, "Hey, I know the Pythagorean theorem, and you don't." Things like that nature. I don't know. That's what I did, at the one party I was at. Yeah. Anywho. All right. Anywho, so other than some of these questions, if even I am not sure what the answer is, we just finished chapter 15. It was a lot of fun. I just found a guess the correlation game online. No, you didn't.
Yeah, I did.
Wow, that's sad. Okay, I'm gonna have to play that after class. But anyway, on Wednesday, we will be reviewing for the exam that will be over the weekends. I would focus on the exam so much more than the this homework. But of course, you're welcome to get started on this homework if you want. All the solutions for 1 to 14 and all of the previous lectures are all online on my YouTube channel. Please like and subscribe. And I will see you all in class on Wednesday. Like and subscribe. Okay, are there any questions? Please like and subscribe. Anything? No, anyone? No?
Sir, what was the name of your YouTube channel again?
It was please. Oh, my name of my YouTube channel? I don't know if it has a name.
I have it actually popped up. It's just if you look up David Berkowitz and math, it'll pop up.
Yeah, otherwise you get the son of Sam.
Okay.
Like it's an orange profile picture with a D in it.
An orange profile picture with a D for David. That's so sweet. Or you can look on my Canvas page and it's the link right at the top. So, any of those work.
Yeah.
All right, everyone. Okay, I'm gonna stop recording now.